Welcome to Bite-Sized Data Science. A while back I had a conversation with my friend Robert Uleman about Pandas data frames. We were talking about the general use of Pandas, data types, and memory usage. The conversation stuck with me, so I thought it would be a good subject to discuss. Let's jump into a notebook. I am using the IBM Watson Studio environment to run my notebook. If you are interested, you can find a link in the description on how to create a free account on that platform. Links to the notebook I'm using here are also available in the description. The first thing I need to do is to get some data. For this, I'm using the Socrata API to access a data source. You can find out more about the Socrata API in videos 19 and 20. I already know the data source I want to access. It is the Chicago accidents that I've used many times. I didn't want to get years of accident records. I tried different time frames and decided on using the last 3 months. The Socrata API can read a maximum of 10,000 records at a time. Since I have more than 10,000 records, I have to loop as many times as needed. The Socrata interface returns a list of records, and all the attributes are provided as character strings. Let's see how big a file is when we save the data as a CSV file. The simplest way to do this is to write the Pandas data frame out as a CSV file and look at its size. We end up with a 19 megabyte file. Then, how much memory is required to keep all this in a Pandas data frame? The Pandas data frame class includes a method that gives us this information. We use it here with a deep equals true argument to get the total usage. Of course, data frames have overhead, so we'd expect it to use more memory than the file. Still, it is surprising that we get 107 megabytes. All the attributes, or columns, are of type objects. Let's convert a few columns, some to int64 and others to float64. For the integer types, I could have easily used int32 or even int16. After converting 8 attributes to numerical values, the new data frame has the same number of rows and columns, but the memory utilization went from 107 megabytes to 92 megabytes for a saving of 14 megabytes. Obviously, the object type has a lot more overhead than int64 and float64, but how bad is it? Let's first take the crash day of week attribute. This attribute includes a single-digit value, which would mean 1 byte if it was encoded in ASCII. Instead, we see that the character representation uses 66 bytes per object. Not surprisingly, the int64 representation uses 8 bytes per object, roughly 8 times less memory. And int32 would use 16 times less memory. If I do the same thing with the latitude attribute, the object type uses more bytes per object, but barely more than the crash day of week. We know that crash day of week is 1 character, and we see here that latitude uses 12. We won't dig any further into this. The lesson to remember is that we can save a lot of memory if we convert numerical attributes from character strings to their proper types. How can we save more memory? We can look at how useful the attributes are. We can eliminate the columns that don't have enough values. In the following example, we set the threshold to 50%. This assumes that if 50% or more of the values are missing, the attribute is not useful. In our case, we eliminated 11 columns and saved an additional 12 megabytes. Overall, we saved 27 megabytes from the beginning of this exercise. This represents a saving of 25%. One more thing. After we do these transformations, we can ensure that the memory used by the data frames we don't need is freed by removing references to them and calling the Python garbage collector. We could go further in reducing the use of character strings in Pandas data frames. For example, we could convert categorical columns to numbers that references the unique values. This is something done in database normalization. Of course, you can also make sure you only keep the attributes you need. See you next time on Bite-Sized Data Science, and don't forget to subscribe.